Good evening. For most of human history, people reported strange lights during storms. Blue fire crawling along ship masts, glowing spheres drifting through the air, brief flashes high above thunderstorms, far above where lightning was supposed to exist. These weren't isolated stories. They came from sailors, pilots, mountaineers, and engineers. People who were trained to observe their environment carefully, and for centuries they were told the same thing. These things were not real. They couldn't be real. And if they were seen at all, it must have been fear, superstition, or a psychological issue. That dismissal wasn't polite skepticism, it was institutional. Studying these phenomena was considered unscientific, career ending, and sometimes absurd by most scientific institutions. Not because the observations lacked consistency, but because the tools to measure them didn't yet exist. So, the phenomena were consigned to the realm of myth. Those who reported seeing such things were labeled as crackpots and thought to be having psychological issues. Any who attempted to study them would quickly find their funding cut. Today, that has changed. We now know that St. Elmo's fire is real. It is a form of electrical plasma. That ball lightning is a physical phenomenon, still not fully explained, and that enormous electrical discharges, called sprites, erupt above thunderstorms, connecting the lower atmosphere to the edge of space. And more importantly, we now understand that Earth itself is electrically alive, wrapped in a global electrical circuit, powered by thunderstorms, coupled to the ionosphere, interacting constantly with space weather and solar energy. What was once called myth is now measurable. Not because nature changed, but because our instruments finally caught up. Tonight, we're going to follow that thread. From phenomena once dismissed as folklore, to the discovery of a planetary scale electrical system, and to a quiet but profound question modern science is now willing to ask: if nature has been running these electrical systems all along, what else might we still be misunderstanding? And what might that mean for the future of technology? So, let's start with a phenomenon that fooled people the longest. Not because it was rare, not because it was subtle, but because it sounded too mythical to be real. For sailors, St. Elmo's fire was never theoretical. It appeared during storms when the air felt charged and the rigging hummed. Blue-white flames would bloom at the tips of masts, along yardarms, even along the horns of cattle or the wings of early aircraft. It didn't burn wood. It didn't consume anything. It just hovered, flickered, and crawled. For centuries, it was considered a sign, sometimes divine protection, sometimes a warning, sometimes the presence of a saint, usually Saint Erasmus, known to sailors as Saint Elmo. The interpretation depended on who you asked, but the experience was remarkably consistent. And that consistency should have mattered. But science had a problem. Fire, as it was understood for most of history, requires combustion, heat, fuel, and oxygen. St. Elmo's fire had none of those, so it couldn't be fire, which meant it couldn't exist. Today, we know St. Elmo's fire is a type of plasma. Plasma is sometimes called the fourth state of matter, not solid, liquid, or gas. It forms when a gas becomes electrically energized enough that electrons are stripped from atoms, creating a mixture of charged particles. Most of you've seen plasma before: neon signs, plasma globes, and the aurora borealis. St. Elmo's fire is a corona discharge, a specific kind of plasma that forms when the electric field in the air becomes extremely strong, usually during thunderstorms, especially around sharp or pointed objects. Sharp objects concentrate electric fields. That's one of the reasons why lightning rods work. When the electric field becomes intense enough, it ionizes the surrounding air. The air itself begins to glow. No burning, no heat-driven flame, just electricity exciting the atmosphere. Thunderstorms act like giant electrical generators. Inside them, ice particles collide, separating charge. Positive charge builds near the top of the storm, negative charge near the bottom. This creates enormous voltage differences between the clouds and ground, the clouds and the clouds, and the clouds and the upper atmosphere. Before a lightning strike ever occurs, the electric field near the ground can become intense enough to ionize air locally. That's when St. Elmo's fire appears. It's not lightning, but it is a warning that lightning conditions are present. Here's where the institutional dismissal matters. Sailors were not physicists. Pilots were not atmospheric scientists. And early science had no instruments capable of measuring local electric field strength in storms, ionized air at low temperatures, and transient electrical phenomena that leaves no residue. So, reports were filed under folklore, religious interpretation, and optical illusions or hallucinations. Even as late as the early 20th century, St. Elmo's fire was treated as a curiosity, not a system worth studying. Which is striking, because it was happening constantly in some of the most dangerous electrical environments humans encounter. St. Elmo's fire turned out to be important for three reasons. First, it demonstrated that plasma can exist naturally at Earth's surface without extreme heat. Second, it showed that the atmosphere can act as an electrical medium, not just an insulator. And third, it hinted that thunderstorms were part of a much larger electrical system. At the time, that idea sounded speculative at best and was generally dismissed as pseudoscience. Today, it's foundational. St. Elmo's fire is now understood as a small, localized expression of a global process, a visible leak in a planetary scale electrical circuit. And once scientists accepted that the air itself could glow without burning, once they accepted that electricity could shape the atmosphere in unexpected ways, it became much harder to dismiss the next set of reports, because these didn't appear on ship masts. They appeared above the storms, high above the clouds, near the edge of space, brief, violent, and completely undocumented by instruments. Until suddenly, they weren't. For decades, pilots were seeing something impossible. Not lightning striking downward, but light erupting upward. Red flashes, branching shapes, vertical columns that appeared for milliseconds above thunderstorms, far higher than any cloud could reach. They were seen at cruising altitude, sometimes above it, and almost no one reported them. Not because pilots weren't seeing them, but because reporting them came with consequences. Commercial and military pilots operate under strict medical and psychological evaluation standards. Seeing things that weren't officially recognized as real meant triggering a review. And that review could mean mandatory psychological counseling, temporary grounding, and permanent loss of flight status. For a pilot, that often meant the end of a career. So pilots learned something quickly. If you saw strange lights above storms, you didn't log it. You didn't mention it. You didn't ask questions. You just flew on. This created a silence that lasted decades. The problem wasn't just stigma. It was physics, as it was understood at the time. Lightning was believed to be confined to cloud to ground and cloud to cloud. The upper atmosphere was thought to be electrically quiet, too thin, too diffuse to support large electrical discharges. And there were no cameras fast enough, sensitive enough, or positioned correctly to capture events lasting only milliseconds. So reports were classified as optical illusions, reflections, night vision artifacts, or some psychological effect due to prolonged exposure to the upper atmosphere. So reports were confined to small talk at parties and quiet talk among colleagues in personal settings, nothing official ever. The breakthrough didn't come from belief, it came from accident. In 1989, researchers testing a low-light camera to study lightning pointed it toward a distant thunderstorm. They weren't looking above the clouds, but the camera caught something anyway. A brief, towering flash extending upward from the storm into the upper atmosphere. It wasn't lightning, it was something else. That footage forced a re-evaluation. Within a few years, similar observations were confirmed independently by ground-based cameras, aircraft, mounted instruments, eventually, satellites. The phenomenon was real, and it already had a name. The names pilots had called it for years: sprites. Sprites are transient luminous events, often shortened to TLEs. They occur high above thunderstorms, typically between 50 and 90 kilometers above Earth's surface. In the mesosphere, far above cloud tops, they are not lightning bolts. They are rapid electrical discharges triggered by powerful lightning strikes below, usually positive cloud to ground lightning, which alters the electric field above the storm. Sprites are plasma, like St. Elmo's fire, but formed in much thinner air under very different conditions. They appear red because nitrogen dominates the upper atmosphere, and nitrogen emits red light when excited electrically at low pressure, and sprites last only milliseconds, which is why they were invisible to the naked eye unless you knew exactly where to look. Sprites shattered a long-standing assumption. The atmosphere was not electrically layered and isolated. It was connected. A lightning strike near the ground could trigger a discharge tens of kilometers above the storm. That meant thunderstorms weren't just local weather systems. They were coupling energy into the upper atmosphere. And that raised a much bigger question. If storms can electrically influence the edge of space, what else are they connected to? Once sprites were accepted, the silence around pilot reports became impossible to ignore. Researchers began quietly collecting anecdotal observations pilots had withheld for years. The stories matched the data. The phenomenon had always been there. Science simply hadn't been ready to hear about it. Sprites are now routinely observed and studied. They are classified, they are modeled, they are measured, and they are recognized as a key component in a much larger electrical system surrounding Earth. Sprites taught scientists something uncomfortable. Not just that the atmosphere behaves in ways we didn't expect, but that entire classes of real phenomena can go unstudied when observation carries personal risk. And that brings us to a phenomenon even harder to capture. One that doesn't stay high above storms. One that drifts through the air, sometimes indoors. And one that, even today, still resists a single explanation: ball lightning. If St. Elmo's fire looked too symbolic to be real, and sprites happened too fast and too high to be believed, ball lightning had a different problem. It behaved badly. It didn't strike like lightning. It didn't stay fixed like plasma in a lab. It drifted, floated, changed direction. Sometimes it moved against the wind. Sometimes it entered buildings. Sometimes it passed through windows without breaking them. And sometimes it exploded. This made it almost impossible to classify. Reports of ball lightning go back centuries. They appear in ship logs, church records, scientific correspondence, eyewitness testimony from engineers, physicists, and meteorologists. And the descriptions are strikingly consistent. Luminous spheres, typically, the size of a grapefruit to a basketball, white, orange, red, or blue, lasting from a few seconds to over a minute, often associated with thunderstorms, but not always coincident with lightning strikes. And yet, for most of modern scientific history, ball lightning was treated as mythology and folklore, not because the reports were rare, but because the phenomenon didn't fit any existing model. Lightning, as understood in classical physics, is a rapid electrical discharge. It happens. It's over. Ball lightning, on the other hand, lingered. It moved slowly. It appeared stable. It sometimes interacted with physical objects. There was no known mechanism that could confine plasma into a sphere, maintain it at atmospheric pressure, and allow it to persist without an obvious energy source. And unlike St. Elmo's fire, it left no consistent physical trace. So ball lightning became something worse than unproven. It became embarrassing. By the early 20th century, openly studying it was seen as unserious. Funding was unavailable, and papers were rejected. Even well-documented eyewitness reports were dismissed as optical illusions, hallucinations, misidentified sparks, or reflections. Some physicists explicitly warned students away from the topic. It wasn't just skepticism, it was stigma. The shift didn't happen because someone finally believed the stories. It happened because instruments began to catch up. In the late 20th and early 21st centuries, high-speed cameras, electromagnetic sensors, and spectral analysis tools improved dramatically. Then, in 2014, something critical happened. Chinese researchers accidentally recorded a luminous sphere during a thunderstorm using spectrometers designed to analyze lightning. They didn't just see it. They measured it. The recorded spectrum showed emissions from silicon, iron, calcium, and elements consistent with vaporized soil. This supported a hypothesis that had existed quietly for years, that at least some forms of ball lightning may involve vaporized material from the ground, energized and structured by electromagnetic fields created during lightning strikes. This was not a complete explanation, but it was the first instrumental evidence that ball lightning was a real physical phenomenon, not a psychological one. Here's what is solid. Ball lightning is real. It has been observed visually, recorded on video, and measured spectrally in at least a small number of cases. It is associated with thunderstorms, though not always directly with visible lightning strikes. It involves plasma or ionized material, and it can interact with its environment in measurable ways. What science does not have is a single unified model. Instead, there are multiple competing hypotheses, including vaporized material models, where lightning strikes soil or other material, creating an energized plasma cloud, electromagnetic confinement models, where microwave radiation traps plasma into a stable structure, chemical energy models involving slow oxidation of energized particles, or possibly electrostatic models involving complex field interactions near conductive surfaces. None of these explanations accounts for every reported behavior, which suggests something important. Ball lightning may not be one phenomenon. It might be a category of related phenomena produced under different conditions by different mechanisms. Ball lightning sits at an uncomfortable intersection within science. It is too rare to study easily, too unpredictable to reproduce reliably, too real to dismiss anymore, and that makes it scientifically valuable because it highlights a blind spot. Our atmosphere can sustain structured, long-lived electrical phenomena under natural conditions we do not fully understand. Taken together with St. Elmo's fire and sprites, ball lightning completes a picture that was invisible for most of scientific history. The atmosphere is not electrically passive. It is active, dynamic, structured, and it operates across a massive scale, from glowing plasma on a ship's mast to luminous structures drifting through the air to massive electrical discharges reaching the edge of space. These are not anomalies. They are expressions of a large global system. Once that realization set in, the question changed. Not whether these phenomena were real, but how they were connected. And that question leads directly to a discovery that reframed everything. The realization that Earth itself operates as a global electrical circuit, not metaphorically, literally. Before we talk about what this system is, we need to clear up a common point of confusion. Because Earth already has something electrical surrounding it, but this is not that. Most people are familiar with Earth's magnetic field. It's generated deep inside the planet by the motion of molten iron in the outer core. It deflects charged particles from the sun. It creates the aurora. It protects the atmosphere from being stripped away by solar wind. That system is magnetic. It is driven by geology. And while it interacts with electricity, it is not itself an electrical circuit. The system we're talking about today is different. It exists in the atmosphere. It is powered continuously, and it involves the movement of electrical charge every second of every day. The global electrical circuit is a planet-wide system in which Earth's surface and the ionosphere act as two conductive layers separated by the atmosphere. Think of it as a spherical capacitor. The ground carries a net negative charge. The ionosphere, about 60 to 100 kilometers above Earth, carries a net positive charge. The atmosphere, in between, normally resists electrical flow. But that resistance is not absolute. Because thunderstorms exist, the basic idea began forming in the early 20th century. Scientists noticed something strange. Even on clear, calm days, far from storms, there was always a measurable electric field between the ground and the air above it. Always. That meant charge was being maintained globally. The question was how? By the mid-1900s, measurements from weather balloons, ground-based electric field meters, early ionospheric studies pointed to a continuous process. Thunderstorms act as electrical generators. At any given moment, there are roughly 1,000 to 2,000 thunderstorms active around the planet. Each one pumps negative charge downward to Earth's surface and positive charge upward toward the ionosphere. Even when storms dissipate, the charge remains distributed globally. The circuit never turns off. Here's the simplified version. Thunderstorms separate charge internally. Lightning discharges some of it locally, but a significant amount is transferred upward and downward, not neutralized. This maintains a voltage difference of roughly 250,000 volts between Earth's surface and the ionosphere. In fair weather regions, away from storms, That charge leaks slowly back through the atmosphere as a tiny, continuous current. You don't feel it, but instruments can measure it. This is why the atmosphere is never electrically neutral. It is always conducting slightly. This is where everything connects. St. Elmo's fire occurs when the local electric field becomes strong enough to ionize air near objects. Sprites occur when lightning alters the electric field high above storms, triggering discharges into the mesosphere. Ball lightning appears to arise under extreme, localized electrical conditions that we still don't fully understand. These aren't isolated anomalies. They are localized breakdowns or expressions of a global system under stress. Visible points where the circuit behaves non-linearly. The global electrical circuit wasn't missed because it was controversial. It was missed because it's subtle. The currents are small, the fields are weak outside storms, and the system spans the entire planet. Its discovery and identification required global coordination of measurements, long-term data collection, high-altitude access, satellite instrumentation, and the realization that things we thought were myths and old wives' tales actually held valid data. Only in the space age could it be fully mapped, and only recently has it been integrated into climate and atmospheric models. This system matters for several reasons. First, it affects atmospheric chemistry. Electrical activity influences cloud formation, aerosol behavior, and the production of trace gases. Second, it links weather to space weather. Solar activity modifies the ionosphere. That changes the circuit, which feeds back into atmospheric electrical conditions. Third, it reframes how we think about energy flow on Earth, not as isolated systems, but as coupled layers, ground, atmosphere, near space, all exchanging charge continuously. What's striking isn't that this system exists. It's that for most of scientific history, it wasn't even considered, because the atmosphere was assumed to be passive, because electrical phenomena were treated as rare exceptions, and because reports that didn't fit existing models were maligned and quietly ignored. Today, none of that is defensible. The Earth is electrically active, always has been. We simply didn't know how to listen. For centuries, people described lights in the sky and fire in the air. They were told those things couldn't exist, not because they violated nature, but because they violated what scientists believed to be true. St. Elmo's fire didn't fit combustion. Sprites didn't fit lightning. Ball lightning didn't fit anything at all, and so they were ignored. Not gently questioned, but actively sidelined, associated with superstition, error, or mental instability, often at real personal cost to the people who reported them. What changed wasn't belief, it was measurement. Once we had the instruments to see faster, farther, and higher, the atmosphere revealed something unexpected. Not a collection of rare anomalies, but an electrical system operating continuously, linking the ground beneath our feet to the edge of space. A system so large and so subtle that it hid in plain sight. Today, we don't talk about these phenomena as myths. We model them, we measure them, we incorporate them into climate science and space weather research, and yet, the story isn't finished. Ball lightning still resists a single explanation. The full role of atmospheric electricity in weather and climate is still being mapped, and the global electrical circuit is only beginning to be understood as a dynamic, interacting system. Since this is the case, we have to wonder, what else is being missed? Because science has not yet developed the tools to identify, quantify, and map it. This has been For What It's Worth. For more interesting information, please like and subscribe.
These lights are caused by charged particles from the sun interacting with the Earth's magnetic field.